Okay, what's up? Welcome back. Today we're talking about duality, finishing out chapter 3. This is where it gets fun. This is the part of the class where I think we start to encounter a lot more interesting and advanced concepts, and also the place where sometimes people start to get a little bit more confused. Hopefully that won't happen here. I don't think it will. I think if you just take things step by step, it shouldn't be too bad. But this is where we're going to get some of the big guns, so to speak. These are powerful tools. So let's start talking about it. It's nothing too crazy. Duality. First thing off, we're going to talk about dual spaces and dual maps. So this is all about linear functionals. Kind of a strange name since we already have an idea of a linear function. The AL suffix is just to distinguish this from a regular linear function. It is a particular and distinguished type of them. So a linear functional on a vector space V is a linear map from V to its underlying field. So a linear map is just an element of the space of linear maps from V to the underlying field. Okay, not too crazy. We can denote, just for short, because we'll talk about these guys so much, we'll call these linear functionals elements of the dual space. So the set of all linear functionals from V to F we'll denote by V prime, and we'll call it the dual space of V. You'll understand why pretty soon. It's essentially just V, but with a slightly different way of looking at it, at least in the nice cases. So before I, ramble too much about that, let's just get into it a little bit. And once you start to see it, I think then my pontificating will be more appropriate. So first off, let's start to talk about the dual space and how it's similar to V. So the idea is that we're essentially going to be able to study what's in V in terms of its dual space. And secretly, we've actually been doing this the whole time. So let's start out with the most basic thing we could look at to see if these things are kind of similar. One of the things that might motivate this, at least. Oops, why is this not drawing me a box the way I want it to? There we go. Which is we could check and see if it has at least the same dimension, right? Okay, so if V prime is going to be sort of like a model for V, a way of looking at V without actually having to deal with V itself, we will hopefully at least have the same, length of bases. That is the same dimension. If it's got any hope of being similar to V, sort of the same thing, then it has to have the same dimension. This is a very straightforward proof. So we know that if V and W are finite dimensional vector spaces, then the dimension of L, VW, is just equal to the dimension of V times the dimension of W. We proved that before. Okay, so if W is equal to the field, the dimension of W, which is just the dimension of the field, is 1. Oh, okay. And we get dim V prime, the dual space. That's just the dimension of, what V prime is. It's the linear maps from V to the underlying field. So that's just the dimension of V times the dimension of the field, which is just dim V. Hey, dim V prime equals dim V. We're done. Nice. All right, so they have the same dimension. So what? Well, we know that all finite dimensional vector spaces with the same dimension are isomorphic. So there is an invertible linear map, a relabeling, that lets you turn everything in V prime into things in V and vice versa. That is, V prime and V, when V is finite dimensional, are just the same vector space, but with things labeled differently. That is, you can think of it like you have a vector space and there's a bunch of stuff in it, and in V prime, you've put stickers on it that look one way, and in V, you just have different stickers on it. So you could take the stickers off and put on new stickers, and then you could, undo that as well. So these are the same. They are isomorphic. We know that now because they have the same dimension. All right. Well, let's start getting into how that isomorphism works. That is, there is actually a very nice, even canonical way of identifying vectors with vectors in V with vectors in the dual of V. So we'll talk about a very nice way to see this. This is the dual basis. So if we take a basis V1 through Vn for a vector space V, necessarily by this finite dimensional and dimension n, then the dual basis of this basis is a new list, same length. We'll write phi1 through phi n, where each phi j is the linear functional on V defined in the following way. Phi j of vk is 1 if k is equal to j, and 0 if k is not equal to j. Notice, since phi j is defined on a basis, it is defined everywhere. By linearity. Okay. i.e., let's just write it out. Phi j of v, well, that's going to be equal to phi j of, a1 v1 plus ... all the way down to an vn for some a1 through an in the field, since you can write every vector v as a linear combination of the basis elements v1 through vn. Okay. By linearity, we can split this out. a1 phi j v1 plus ... all the way down to an phi j vn. But hey, by definition, you only get 1 if k is equal to j, and you get 0 otherwise. Oh, okay, so we know what this is going to be. Well, this will just be aj phi j of vj. All the rest of them are zeros, and phi j of vj is 1. So this is just aj. Hey, wait a second. We've actually seen this linear functional flying around everywhere, though we haven't acknowledged it. That is, when you take a vector v and you write it in terms of a linear combination of a basis, then the coefficients are the values of these dual basis vectors. Oh, these are just the functions that take a vector v and spit out the coefficient next to the corresponding basis element that the linear that this dual basis vector is paired with. So see, phi j is paired with vj, so it spits out the coefficient next to it, aj. Oh, it's like the easiest kind of linear functional ever. You know, it makes perfect sense. We've been seeing this thing all the time, just hidden every time we write a vector v as a linear combination of a basis. The thing that sends that vector to the corresponding coefficient next to the basis element is part of the dual basis of, or is the values of the dual basis vector corresponding to that basis vector on that vector we started with. Kind of a mouthful, but we'll get used to it. So let's look at these a little bit more. All right, let me make a little bit clearer the thing I just said. In case it doesn't seem fully nice, let's formalize it into a result. So let's suppose that v1 through vn is a basis for a vector space V. Necessarily then, V is finite dimensional and has dimension n. All right, we can take its dual basis, phi1 through phi n. Then what the claim is that V is equal to phi1v, v1, plus ... all the way down to phi n v, vn. For each v, i.e., the values of the dual basis at that vector v give you the corresponding coefficients in the linear combination that lets you write v in terms of the basis v1 through vn. Proof. Let's do it. Okay, so all we have to do is the following. Since v1 through vn is a basis of v, there exists a1 through an in the field such that v is equal to a1 v1 plus dot 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 all the way down to an vn. That is, you can write v as a linear combination of v1 through vn. It's a basis after all. Okay, so by linearity, we get phi j of v is phi j of a1 v1 plus dot 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 all the way down to an vn, which is just a1 phi j v1 plus dot 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 all the way down to an phi j vn. And from the definition of the dual basis, all of these are 0 except for the one with phi j. And you just get aj phi j vj. But for phi j of vj, you get back 1. So this is just aj. So we get this for each j in 1 through n. So this says, well, v, that's a1 v1 plus dot 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 all the way down through an vn, but each of these a's is equal to, well, we just got phi j is equal, or phi j of v is equal to aj. So we can rewrite each of these a's as a phi of v. So this is phi 1 of v, v1 plus dot 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 all the way down to phi n of v, vn. Hey, look at that. All this says is that you can write a vector in terms of a basis where the coefficients in this linear combination that let you write the vector in terms of the basis are the values of the corresponding dual basis. That is, the linear functionals paired with each basis vector evaluated at the vector we're trying to write as a linear combination. Pretty neat. Nothing too crazy. Okay, so we should at least double check one thing really quick. We should think about this carefully. So we've been calling this a dual basis. We've proved that you can do this nice decomposition. That is, we've shown that these dual basis vectors just give you the coefficients in a linear combination in terms of the basis vectors. But are they actually a basis as well? Yes. So if v is finite dimensional, then the dual basis of a basis of v is indeed a basis of the dual space. Pretty cool. Okay, so dualizing takes bases to bases. Ooh, that sounds nice. Okay, so let's prove this. Suppose that v1 through vn is a basis of v. Now, let's let phi 1 through phi n denote the corresponding dual basis. Okay, so we got a basis. We can get our dual basis paired to this basis. All right. For linear independence, suppose that a1 through an in the field are such that a1 phi 1 plus dot 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 all the way down to an phi n is equal to 0. Think about this really quick. 0 is in the linear functionals from v to the field, which is v prime. That is, I'm taking a linear combination of things in the dual space v prime, so I should get something back in the dual space. So the 0 in here, this is the map 0v equals 0 for all v in big V. Okay, so this is the 0 map. All right, cool. But then, think about this. A1 phi 1 plus dot, 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 all the way down to an phi n. This is a linear functional, so this is a linear map from V to the field. I could evaluate it at, say, Vj. Well, this is the same as 0. I'll write this even on the other side just for convenience. So here, let me move this slightly. There we go. Oof, the wonders of technology. But then 0 in V is equal to the 0 map evaluated at Vj, which is just the same as this thing, this big old linear combination of our dual basis vectors evaluated at Vj. But hey, we know what this is. This is, well, all we have to do is pull everything together. Okay, so think it through really quick. What's going to happen? Well, I'll get A1 of phi 1 of Vj plus or I'll even write the dot, 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 dots instead of writing A2 and so on, all the way down to An of phi n of Vj. That is, if you take the sum of linear functionals and you evaluate it at something, then that is the sum of the evaluations. That's how it's defined, right? Okay, but hey, all of these are 0 except for one of them, which is 1. We get Aj, phi j, Vj, which is just Aj. So, since this holds for all j in 1 through n, this says A1 equals dot, 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 all the way down through An equals 0, since we just got Aj is equal to 0 by evaluating this linear functional at Vj. Okay, so it's linearly independent. Nice. Thus, phi 1 through phi n is a linearly independent list in V prime of length dim V prime, so it is a basis. Oh, cool. We just used two previous results. So first thing first, we used this one right here, essentially, basically the same line of argument right there that said that, hey, phi j of V, well, that gives you the corresponding coefficient. So if you take V to be Vj, then it would just give you back 1, right? We're doing the same kind of trick right here. Oh, okay, cool. Now we get a linearly independent list, and by one of the first things we proved, that the dimension of V prime is the same as the dimension of V, we have a linearly independent list of length dim V prime. So we have a basis. Excellent. We can take bases, two bases, by dualizing. Very cool. Let's look a little bit more at all of this and see if we can get a better sense for what's going on. Okay, so why do I care about dual spaces? What are they going to do for me? It turns out that they'll do a lot, and we'll get a much more advanced perspective on them as time goes on. But one of the main things that they do is they let us take linear maps and turn them into linear maps that are perhaps easier to work with. Let me explain. So, the idea is that we could take a linear map from V to W and produce a dual map. So this is going to be the linear map in called T prime, just like we write the dual space as V prime, between the dual space of W and the dual space of V, defined by the following. T prime of a linear functional on W, that is a map from W to the underlying field, is just that map composed with T. Here's sort of the picture to have in your head. So here's like the visualize it sort of idea. Okay, basic gist of it. So t takes v to w. T does that. Okay. Now we can take something from v to the field, and we can take something from w to the field, right? Okay, t prime will take something from there and turn it into something here. So something that takes w to the field and turn it into something that takes v to the field in the following way. So we take some phi right here. All right. And essentially, I'm going to do like a small erase right now, just to make this hopefully a little bit clearer. Since I could just draw that arrow as pointing at this f right here, which might make things a little bit nicer looking. Let me get back to my pen. And essentially, here's the idea. By following this one and then that one, I can do the exact same thing. So first I do t, that takes me from v over to w, and then I do phi. Oh, okay, cool. This is t prime. Nice. You're just following a path. So that makes some sense of why we're reversing the arrows here, right? T takes v to w. The thing going on here is that t prime takes w prime to v prime. That is, it takes things like this and turns them into things like this. Oh, cool. Okay. So why might this be nice? Notice t prime basically flops the range, or I shouldn't say the range, I should say the domain and codomain of t around. Technically, it flops and dualizes. So let me write that U a little bit nicer. Dualizes. But since v and v prime, also w and w prime, are isomorphic if finite dimensional. This part basically is just relabeling. So that's kind of the idea. Okay, t prime, it just basically takes t, and t has a domain and a codomain. T prime takes the codomain of t and makes it into the domain by dualizing, and it takes the domain of t and makes it into the codomain and dualizes. All right, now if v and w are both finite dimensional, we now have a map essentially from w to v up to isomorphisms of w and v. Whoa, that's actually really cool. We kind of just flop domains and codomains. Sometimes it can be really inconvenient to work with a map from v to w, but very convenient to work with a map, say, from w to v. This says, here's a way to do it, up to some isomorphism. Okay, so let's think about dual maps and talk about some basic algebraic properties of them. All right, so first things first, we should think about linearity. Well, actually, let me even write this up here, just for linearity. So I'm claiming that t prime is in L w prime v prime. Notice the claimed linearity is a consequence of t primes, I should say of the, I don't want to say t primes because it will look like I'm putting double primes for the apostrophe, of the definition. of t prime. It is just a composition of two linear maps. See, this is something in W prime, right? So it's a linear map from W to the field, and T is a linear map from V to W. You put them together, you should get another linear map, right? Okay, cool. So it's definitely sending linear maps to linear maps. Nice. That makes some sense. Now, is it sending linear maps to linear maps in a linear fashion? We should double check that. So the way to do that is very, very straightforward. All you're going to have to do is just do the very basic idea of saying, hey, let me draw like a little squiggle over here. Let's take t prime of phi plus psi, or let me make that look like a psi, not a phi. Psi. Well, this is just phi plus psi composed with t. Okay, so that's just phi composed with t plus psi composed with t, which is just t prime of phi plus t prime of psi. Oh, okay, cool. So we've got additivity. Homogeneity, super easy as well. T prime of lambda phi. Well, that's just lambda phi composed with t. But hey, this is just lambda times phi composed with t, which is just, hey, check it out. Look at that. Lambda times t prime of phi. Look at that. So we've got homogeneity, and we've got additivity, we've got linearity. Okay, cool. So it is indeed a linear map. T prime is at least, right? T prime is indeed a linear map. Nice. Now, let's prove some properties of it. So let's suppose that T is a linear map from V to W. Then, the dual of a sum for any S in LVW, we take S plus T, take its dual map. It is the sum of the dual maps. Okay, pretty easy. Take lambda T, dualize it, you get lambda times T's dual. Take the dual of ST, you get, T prime S prime. Let's look at this. So, here's the gist. A and B, easy. All we have to do is follow definitions. So just think about it real quick. Okay, so A. Let phi be an element of W prime. Then S plus T, that dual map of phi, is just defined to be phi composed with S plus T, which, hey, we can do some composition right here. Nothing crazy is going on. This is phi of composed with S plus phi composed with T, which is just S prime phi plus T prime phi. Oh, okay. So if for all phi in W prime, S plus T prime on phi, and S prime on phi plus T prime on phi, if they agree at every point, then they are the same map. Oh, okay, cool. So they're the same. B, very similar. Let's let phi be in W prime and lambda be in the field. Then lambda T prime evaluated at phi is, by definition, phi composed with lambda T. Oh, okay. But by the linearity of phi, we can pull that outside. Lambda of phi composed with T, which is just lambda T prime of phi. Oh, okay. So this equality follows from the linearity of a linear functional. Oh, okay, cool. So you can pull out constants. Nice. C is perhaps the one that's actually kind of interesting and potentially a little bit harder to prove. Why does the order flip? What on earth is going on there? Well, let's just do it the same way. So let's do this. So let's see. Oh, here we've got, went a little bit too far. Okay, so here we've got S in WU. Now, to be clear, we're using potentially a different space there. So we should be a little bit careful here. All right, so suppose S is in LWU. All right. And let's take some phi now in U prime. Then we'll just do the same type of calculation. All right. ST prime, the dual map of ST, evaluated at that linear functional, is by definition that linear functional composed with ST. Okay, but hey, we know that this is just the linear functional composed with S, that whole thing, composed with T. But now we just have to write out what this is. The linear functional composed with S, that'll be something, but now I'm composing with T, so this is T prime of phi composed with S, right? Functional composed with T, that is T prime of whatever that functional is. Oh, okay, cool. Now we're doing the same thing yet again. I get T prime of S prime of phi, which is just, hey, look at this. It's T prime S prime of phi. So that's where that order flip comes from, because we're flipping when we do our compositions. Nice. Very cool. This may remind you of something. It may remind you, say, of transposes. When you take the transpose of AB, you get B transpose A transpose, right? There will be a connection that we'll talk about soon. So let's keep going a little bit. Now that we've got maybe a reason to study dual spaces, we've got some sort of an idea of what they might do. They might let us carry maps from a vector space to a field over to a different vector space to a field using a linear map between them. That is, we can kind of switch domains and codomains around using dualization. This will prove to be very, very powerful. And even better, this dualizing process has lots and lots of nice properties. So, like I said, let's look at a little bit more. All right, so since we're breaking today into two parts, or since we're breaking the section into two parts, today's just one part, we will finish up at kind of a strange place, but we'll end with a little bit more discussion. So we're going to talk about another distinguished subspace that you can associate to a linear map. So the null space and range of the dual of a linear map will be what we talk about. And the way that we end up doing this is by using a totally different subspace. All right, here's the idea. Having dual spaces lets us get from subspaces other subspaces. So take U to be a subset of V, could potentially be a subspace. The annihilator of U, which we'll denote by U0, is defined to be the set of linear functionals such that phi of U is 0 for all U's in U. Here's the idea. If we take any old subset of V, then U0 is a subspace of the dual space. Oh, cool. Now, if V is finite dimensional, then the dual space is isomorphic to V, and so this subspace, the annihilator, is isomorphic to some other subspace of V. So this lets us take subsets and get at subspaces somehow associated to them. We'll prove this really quick, get used to annihilators a little bit, and what we'll end up doing is we'll use annihilators to characterize the null space and range of the dual of a linear map. So the same way that we took linear maps between vector spaces and we got at these distinguished subspaces of their domains and codomains respectively, called the null space and the range. As every linear map gave rise to a pair of subspaces. One of them was the null space, one of them was the range. All right, we can do the same thing for the dual map of a linear map. And this will tell a very, very compelling story. So let's start it out just by getting used to the annihilator. So U0 is a subspace of V. The annihilator is a subspace of V prime, not V. Talking too quick. So by definition, all we have to do to show that this is a subspace is show that it's a vector space in its own right. All right, we need to only show three things. First, we need to show that the 0 is in the annihilator of U. U0 is closed under addition, and that U0, the annihilator of U, is closed under scalar multiplication. Okay, so first off, note that 0 in V prime, which if you'll recall, is just the set of linear maps from V to its underlying field, is defined by 0 of V is the 0 element in the field for all V in big V. So 0 of U is equal to 0 for all U in big U, and 0 is then an element of the annihilator. The annihilator is just all the functionals that zero out everything in U. Hence the notation U superscript 0. It's all the things that send U to 0. Oh, cool. Okay. Now, suppose phi and psi are in the annihilator of U. Then phi of U is 0 and psi of U is 0 for all little u's in big U. Hence, we have, now we just have to show that there's sums in there. Okay. Phi, okay, sum them together, plus psi. Oh, my psi looks a little weird right there. Psi of U. Well, by definition, this is just phi of U plus psi of U, which is just 0 plus 0, which is 0. So phi plus psi is in the annihilator as well. Finally, suppose phi is in the annihilator of U and lambda is in the field. Then lambda phi of U, well, this is just lambda times phi of U, which is just lambda times 0, which is just 0. And this holds for all U in big U. Okay, so lambda phi is in the annihilator as well. Oh, cool. Okay, very nice. So the annihilator of any subset of a vector space is itself a subspace of the dual space of that vector space. A lot of these sentences are kind of a mouthful like that, but they're not that terrible to understand once you get into the, the definition of it. After all, the annihilator is just all of the linear maps that send everything in the set being annihilated to the 0 element of the field. Okay, Nothing too crazy. Let me give you a little bit of perspective to kind of end today with. So I'm going to zoom out a little teeny bit. Kind of draw a quick little line. Okay, so here's the kind of idea of it all, if you want to think of it like that. We can look at vectors and the subspaces they span. Okay, so we can, let me draw a picture if you want to think about it like this. You can think of, and this is sort of like a theme I've tried to talk about throughout the class, you can look at, say, the ways that you can sort of try to take a single vector and break down the vector space into chunks using one vector. So let me just kind of try to draw that picture. So you've got, this is span V, and over here we've got some little v. Okay, so if you're breaking down a vector space into the smallest vector spaces that you can have inside of it, you're looking at the spans of single elements. All right, so you can break down a vector space into little vector spaces. We've talked about how to do that. We've talked about how to take the little vector spaces and put them back together to get the big vector space. We've talked about how to do this in a way with no redundant information. That was when the sum is direct, to sort of see how you can build a big vector space out of small pieces. In particular, if you build them out of the smallest possible pieces, then you end up talking about bases. Okay, cool. Here's the idea of dual spaces. The idea of a dual space is to invert this. So here's the picture now, and I will try to explain why this is what we're doing. Here's the gist. Now we've got the span of V. Okay, so this single small subspace, all right, easy enough. You've got your little V right down here. Let me make that V look nicer over in the other one. Okay, so you got your V and your span V, all right. Now, here's the idea of what we'll do, is we'll take, essentially, everything except for this line. So the idea is to find something in V prime, so an element of the linear maps from the vector space to the underlying field that is 0 except on span V. So this will turn into the null space of some phi, and this little chunk right here, this very important little subspace, will turn into, well, not the range, but this is the complement of the null space. That is, this is the place where phi is non-zero. So kind of the idea of this is that you can study specifically little lines in a vector space, the smallest subspaces you can have, or instead, you could study things that are 0 except on those lines. Sort of think of it like taking this picture and inverting the contrast. Actually, I could probably do that right now if I just, might have been an easier way to do this. So here. Oh, why is it not inverting right? Weird. The white part, oh, it's because the background is black here. Well, I don't know if that's all that helpful. But look, it's like if you inverted it, and so now this is the only place where you have something that's non-zero. Maybe that's not as helpful. There we go, whatever. All right, but that's basically the idea of it. Think about this. Can we always do this? Well, if you have a vector, you could certainly take an element of a dual basis that uses that vector as part of the basis, right? After all, a list with just one element is linearly independent as long as that element isn't 0. Okay, cool. So you can form a basis using that linearly independent list, which just consists of a single vector, right? And then take a dual basis of it. All right, this will just be 1, or the first element of this dual basis will be 1, precisely when the thing you plug in is the vector you started with. So if you look at something in the span of that vector, you'll just get the corresponding coefficient next to that vector when you write something in its span. That is, things in the span of a single vector are just stretches of that vector. So you'll get the stretching factor. All right, and anything outside of there, you'll get 0 on. So this is possible. We'll use this technique to our advantage in a big way in what is to come and throughout the rest of the class. But for now, let's leave it there, and I'll see you next time.